Bismillahirrahmanirrahim. Our today's lecture is about complements. The concept of complement is very important in digital systems. Complements are used to represent negative numbers in digital computers. Negative number contains a negative sign. So if we include a negative sign in the storage of negative number, it will require more memory space. To conserve memory, we use the concept of complements to represent negative numbers. So digital systems use complements to represent negative numbers. There are three forms to represent negative numbers in digital systems: sign magnitude form, ones complement form, and twos complement form. The most widely used form is twos complement form to represent negative number because it is more efficient. Why complements? Complements are important because they permit the representation of negative numbers in digital system. They allow to perform subtraction through addition. There is no need to include a separate logic for subtraction. The method of twos complement arithmetic is commonly used in computers to handle negative numbers. There are two types of complements in each base R system: diminished radix complement and Radix complement. Diminished radix complement referred to as R minus 1's complement, while Radix complement is referred to as R's complement. R represents the base or radix of the number system. For example, the base of decimal number system is 10. So the Radix complement of decimal number system is 10's complement. R is 10. So replace R by 10. So this becomes 10's complement. And R minus 1, 10 minus 1 is 9. So in decimal number system, 10 minus 1 is 9. So the diminished radix complement is 9's complement. The base of binary number system or radix of binary number system is 2. So the Radix complement in binary number system is 2's complement, and the diminished radix complement in binary number system is 1's complement, because R minus 1, 2 minus 1 is 1. So it becomes 1's complement. In octal number system, we have 8's complement and 7's complement. 8's complement is the Radix complement, while 7's complement is the diminished radix complement in octal number system. In base 3 number system, the base is 3, so the Radix complement is 3's complement, while the diminished radix complement is 2's complement in base 3 system. How to compute diminished radix complement or R minus 1's complement? Let n be the n-digit number in base R. The diminished radix R minus 1's complement is given as R raised to power n minus 1 minus n. Here R is the base, this small n represents the number of digits, and this capital N represents the number for which we are going to compute diminished radix complement. For decimal number, R is equal to 10 and R minus 1 is 9. So 9's complement of an n-digit number, 9's complement of an n-digit decimal number will be 10 raised to power n minus 1 minus n, the number. Remember, 10 raised to power n represent n zeros and a single 1. And 10 raised to power n minus 1 represent a number that is consist of n nines. For n is equal to 4, 10 raised to power 4 minus 1 equal to 4 nines. 9,999. To find 9's complement of an n-digit number, subtract each digit from 9. Example, 9th complement of the decimal number 3905. This is a 4-digit number, so subtract each digit from 9. So 9 minus 5 is 4, 9 minus 0 is 9, 9 minus 9 is 0, 9 minus 3 is 6. So this is the 9th complement or diminished radix complement n base 10 of this number, this decimal number. For binary number, r is equal to 2, r minus 1 is equal to 1. So one's complement is the diminished radix complement in binary number system. So one's complement of an n-bit number will be 2 raised to power n. Here 2 is the base of binary number system, is n, the small n represent number of digits and number of bits, minus 1 minus n the number. The binary of 2 raised to power n represent a number that is consists of a single 1 and n zeros. The binary of 2 raised to power n minus 1 consists of n ones. So for example, for n is equal to 8-bit number, the binary of 2 raised to power n minus 1 is this number 8 ones in binary. To find one's complement of an n-bit number, subtract each bit from 1, or change all ones to zeros and all zeros to 1. Example, one's complement of 1011. This is a binary number, and the one's complement of this is this number. So 1 minus 1 is 0, 1 minus 1 is this 0, 1 minus 0 is 1, and 1 minus 1 is 0. So I'll replace these two ones by these two zeros, and this 0 by this 1, and this 1 by this 0. So this is the complement of this binary number, one's complement. To find r minus 1's complement or diminished radix complement of an n-digit number in base r, subtract each digit from r minus 1. This is a general form. For binary number system, r is equal to 2 and r minus 1 equal to 1. So subtract each digit from 1 to compute 1's complement. For decimal number system, r is equal to 10 and r minus 1 is 9. Subtract each digit from 9 to compute 9's complement in decimal number system. For octal number system, r is equal to 8 and r minus 1 equal to 7. So subtract each digit from 7 to compute 7's complement in octal number system. For base 3 number system, r is equal to 3, base the radix is 3, r minus 1 is 2, so the diminished radix complement is 2's complement. To compute 2's complement in base 3 number system, subtract each digit from 2. Radix complement or r's complement. To obtain r's complement, add 1 to the r minus 1's complement. For example, let n be the n-digit number in base r. The r's complement is given as r minus 1's complement plus 1. So this factor represent r is to power n minus 1 minus n. This represent the diminished radix complement, and plus 1. So it represent radix complement when we add 1 to the diminished radix complement. This plus 1 and minus 1 cancel out each other, and we left with r raised to power n minus this capital N, the number. So r raised to power n minus n. For n not equal to 0, and the radix complement is 0 if the number is 0. To obtain r complement, add 1 to the r minus 1's complement. Examples. In binary number system, we have 1's complement and 2's complement. To find 1's complement of binary number, change all zeros to 1's and all 1's to 0, or subtract each digit from 1, each bit from 1. 1's complement of 1011 is 0100. These two ones is replaced, changed by these two zeros, and this 0 is replaced by or changed by this 1, and this 1 is replaced by this 0. And to find 2's complement, add 1 to the 1's complement. 2's complement of the given binary number 1011 is equal to its 1's complement plus 1. So this is 0101. In binary addition, keep in mind, note 1 plus 1 is equal to 10. So you have to carry this 1 to the next bit position. Sum, this is the sum, 0 is the sum, and carry is 1. This is the carry. Decimal number system. In decimal number system, r is equal to 10. So we have 9's complement, r minus 1's as r minus 1's complement, r diminished radix complement, and 10's complement, r's complement, or radix complement. To obtain 9's complement of a decimal number, subtract 8 digit from 9, and to obtain 10's complement, add 1 to the 9's complement. 9's complement of decimal number, for example, this 4563 is 5436. 9 minus 3 is 6. 9 minus 6 is 3. 9 minus 5 is 4, and 9 minus 4 is 5. And 10's complement of the same number is obtained by adding 1 to its 9's complement. So this is the 9's complement, and we add 1 to obtain the 10's complement. So 5437 is the 10's complement. Base 3 number system. In base 3 system, we have r minus 1 is equal to 3 minus 1, 2. 2's complement as diminished radix complement, and 3's complement as radix complement. To find 2's complement, subtract each digit from 2, and to find 3's complement, add 1 to 2's complement of a base 3 number. 2's complement of, for example, 2's complement of 2102 in base 3 is 0120. So 2 minus 2 is 0, 2 minus 0 is 2, 2 minus 1 is 1, and 2 minus 2 is 0. So 0120 is the 2's complement in base 3 of this given number. 3's complement is obtained by adding 1s to the 2's complement. So this is the 2's complement, 0120, and we add 1. So we get 0121. So this is the 3's complement, or the radix complement in base 3, and this is the 2's complement or diminished radix complement in base 3 of the given number. Find 1's complement and 2's complement of the following 8-bit binary numbers. So these 5 numbers are given 8-bit binary numbers. So the 1's complement of this number, change all zeros to 1 and all 1's to 0. So this is the 1's complement. This 1 is changed to this 0. These 6 zeros are changed to these 6 1's, and the last one is changed to 0. So this is the 1's complement. And 2's complement, add 1 to the 1's complement, so we get this number. This is another number. So this is the 1's complement, and this is the 2's complement. This number, this is the 1's complement, and this is the 2's complement. 0 0 0, all zeros, so all 1's in 1's complement, and all zeros in 2's complement. 1 0, so this is the 1's complement. Change all zeros to 1 and all 1's to 0, and add 1 to this, we get this number. In decimal number system, we have 9's complement. So find 9's complement, the 8-digit decimal numbers. So subtract each digit from 9. So this is the 9's complement of this number, this is the 9's complement of this number, and this is the 9's complement of this number, and this is the 9's complement, this is the 9's complement of this number. Find 10's complement of the following 6. These are 6-digit numbers. So the 6-digit numbers. So find the 9's complement and add 1s to the 9's complement. So we get this number. Or subtract the first non-zero digit from 10 and the remaining digits from 9 to compute tens complement. This is an alternate method. So this is the tens complement of this number. This is the tens complement of this number. So look, the alternate method. This is the first digit, non-zero digit. So the zero. So subtract this digit from 10. So this becomes 9 0 0 0 0 0 and 0 0. So the tens complement is 0 0 0 0. Signed number. Representation of signed numbers. A signed binary number consists of both sign and magnitude information. The sign indicates whether the number is positive or negative, and the magnitude is the value of the number. There are three forms in which signed integer whole numbers can be represented in binary: signed magnitude, 1's complement, and 2's complement. Of these, the 2's complement is the most important, and signed magnitude is the least used form. The signed bit. The leftmost bit in a signed binary number is the signed bit, which tells whether the number is positive or negative. A 0 signed bit indicates a positive number, and a 1 signed bit indicates a negative number. For example, look at this 8-bit number. This is a signed binary number. So these 7 bits are the magnitude bits, and the last bit is the signed bit. The signed bit is 0. So this is a positive signed number. If the signed bit is 1, then it will become a negative signed number. Signed magnitude form. In signed magnitude, the leftmost bit is the signed bit and the remaining bits are the magnitude bits. For example, this is the magnitude bits and this is the sign bit. This is the sign bit and these are the magnitude bit. If the sign bit is 0, so it is a positive number. If the sign bit is 1, then it is a negative number. The magnitude bits are in true uncomplemented binary for both positive and negative numbers. In the signed magnitude form, a negative number has the same magnitude bits as the corresponding positive number, but the signed bit is 1 rather than 0. The signed bit for negative number is 1. The magnitude bits remains the same as in positive signed number. For example, the decimal number plus 25 is expressed as an 8-bit signed binary number using signed magnitude form as 0 1 0 0 1 1 1. So these 7 bits are magnitude bits and this is a signed bit, so it's a positive number. The decimal number of minus 25 is expressed as 1 0 0 1 1 0 0. The signed bit is 1 and the magnitude bits are the same as for plus 25. One's complement form. Positive number in one's complement form are represented the same way as positive signed magnitude numbers. Negative numbers, however, are the one's complement of the corresponding positive numbers. For example, using 8 bits, the decimal number minus 25 is expressed as the one's complement of plus 25. This is plus 25 and this is the one's complement. So these bits represent the minus 25 in one's complement form. This is the one's complement. This is the one's complement of this number. So this one is replaced by 0. This is 2 zeros is replaced by 2 1. The 2 1s are replaced by 2 zeros, and the 3 zeros are replaced by 3 1s. In the one's complement form, a negative number is the one's complement of the corresponding positive number. 2's complement form. Positive numbers in 2's complement form are represented the same way in the signed magnitude and 1's complement forms. In 2's complement form, a negative number is the 2's complement of the corresponding positive number. To represent minus 25 decimal number in 2's complement form, in 2's complement of plus 25. So this is the binary of plus 25. Again, this represents the sign bit, inverting each bit to take its complement and adding 1 to get its 2's complement. So minus 25 is, this is the representation of minus 25 in 2's complement form. This is the 2's complement of plus 25, of the binary of plus 25. Example, express a decimal number minus 39 as an 8-bit number in sign magnitude, 1's complement and 2's complement form. First write the 8-bit number for plus 39. So this is the 8-bit number for plus 39. This is the sign bit and this is the magnitude bits which represent 39. In the sign magnitude form, minus 39 is produced by changing the sign bit to 1 and leaving the magnitude bit as they are. The number is, so look, the magnitude bits in minus 39 and plus 39 are the same. The only difference is the sign bit. In plus 39 the sign bit is 0 and in minus 39 the sign bit is 1. In the 1's complement form, minus 39 is produced by taking 1's complement of plus 39, of the binary of plus 39. So this is the binary of plus 39. So the 1's complement along with the sign bit. So this is the 1's complement. In 2's complement form, minus 39 is produced by taking 2's complement of the plus binary of the plus 39 along with the sign bit. So this is the 2's complement of this number, so it represents minus 39. So in sign magnitude form, this is minus 39. In 1's complement form, this is minus 39. These bits represent minus 39. And 2's complement form, this is the representation of minus 39 decimal. Decimal value of sign numbers. In sign magnitude form, to compute decimal values, if a number is given, a binary number is given sign magnitude form, so to compute its decimal equivalent, we sum the weights in all magnitude bit position where there are ones and ignoring those position where there are zeros. The sign is determined by examination of the sign bit. 1's complement decimal values of both positive and negative number is in 1 complement form are determined by assigning a negative value to the weight of the sign bit, summing all the weights where there are ones and adding 1 to the result. 2's complement decimal values of positive and negative numbers in 2's complement form are determined by summing the weights in all bit position where there are ones and ignoring those positions where there are zeros. The weight of the sign bit is given a negative value. Examples. So determine the decimal value of this 8-bit sign binary numbers expressed in sign magnitude. So these two numbers is given, so they are expressed in sign magnitude form. So look at this number, the sign bit is 1, so this is a negative number, and the sign bit in this number is 0, so this is a positive number. So these are the weights of the magnitude bits. This is the given sign binary number, sum of weights of magnitude bits where there is 1. So 2 raised to power 4, because this bit is 1, so 2 raised to power 4 plus 2 raised to power 2 because this bit is 1, and 2 raised to power 0 because this bit is 1. So 16 plus 4 plus 1, so it's equal to 21. 21 is a positive number or negative number, so we examine the sign bit. So the sign bit is 1, therefore the decimal number is minus 21. So this is the decimal equivalent of this sign binary number is minus 21. This is a negative number. In this number the sign bit is 0, so it is a positive number. These are the weight of magnitude bits. This is the sign bit is 0, so the number is positive. Sum of weights of magnitude bit where there is 1. So here is 1, so 2 raised to power 4. Here is 1, 2 raised to power 2, and here is 1, 2 raised to power 0. So 16 plus 4 plus 1, 21. So the number is 21. The sign of this 21, to find the sign of this 21, we examine the sign bit. The sign bit is 0, so it is plus, positive number. The sign bit is 0, therefore the decimal number is plus 21. Determine the decimal values of signed binary numbers expressed in ones complement. So these numbers are expressed in ones complement form. Again, the sign bit is 0, so this is a positive number, and the sign bit is 1, so this is a negative number. These are the weights in ones complement form. We assign negative value to the sign bit, weight of sign bit. So the weight of sign bit is negative. So these are the weights of magnitude bits. This is the signed binary number, sum of weights where there is 1. So here is 1, so 2 raised to power 4. Here is 1, 2 raised to power 2. Here is 1, 2 raised to power 1. And here is 1, 2 raised to power 0. So 8 sum of weights where there is 1. So this is 16 plus 4 plus 2 plus 1. So this is equal to plus 23. Plus 23. So add 1. So we add 1 to the result. Add 1. So 23 plus 1 is equal to 24. For this number, this is a negative number because the sign bit is negative. So these are the weights. Again, this is ones complement form. So we assign a negative value to the sign bit. So minus 2 raised to power 7. This is this given signed binary number, and sum of weights where there is 1. So here is 1, so minus 2 raised to power 7 plus 2 raised to power 6, because here is 1 and 2 raised to power 5, here is 1 and here is 1. So we add the weights where there is 1. So this is minus 128 plus 64 plus 32, 2 raised to power 5 32 and 8. So this is equal to minus 24. So minus 24 add 1. So we add 1 to the result. Minus 24 plus 1 is equal to minus 23. So this is what the decimal values of signed binary numbers in ones complement form. In two's complement form, the decimal values, how to compute the decimal values. So in this example, again we have two numbers. We have given these two numbers. So weights are given. The weight of sign bit, this is sign bit, this is a positive number, this is a negative number because the sign bit is 1. So the weight of sign bit is negative. So sum of weights where there is 1, so this is the sum of weight and it's equal to plus 86. And this example, this is a negative number because the sign bit is 1. So add weights where there is 1. So minus 2 raised to power 7 plus 2 raised to power 5 plus 2 raised to power 3 plus 2 raised to power 1. So it is equal to minus 86. So this is the decimal equivalent of this given signed binary number. Range of signed binary numbers for two's complement signed number. The range of values for n bit number is given as minus 2 raised to power n minus 1 to plus 2 raised to power n minus 1 to minus 1, where in each case there is one sign bit and n minus 1 magnitude bits. So that's why the n minus 1. For example, with 4 bits we can represent number in two's complement ranging from minus 8 to plus 7. Similarly, with 8 bit we can go from minus 128 to plus 127, and with 16 bit we can go from minus 32,768 to plus 32,768. Summary: complements are used to represent negative numbers and to perform subtraction in digital computers. In binary number system we have ones complement and two's complement. To find ones complement, change all zeros to 1 and all ones to 0. Two's complement is obtained by adding 1 to the ones complement. In decimal number system we have nines complement and tens complement. To obtain nines complement, subtract each digit from 9, and to obtain complement, add 1 to the 9th complement. Digital system uses 2's complement to represent negative numbers and to perform subtraction because it is more efficient. It's all for today. Thank you very much.